Welcome to qnawire.
This problem has a ton of information given at the beginning, so please reference the problem to find that information. I'll write down what I need when I need it. So we're given a radioactive decay sequence from uranium-234 to thorium, to radium. And with the number of nuclei decayed by the differential equation where this is the decay constant for uranium to thorium, and is the decay constant from thorium to radium. Okay. Starting with 10 nuclei, 10 uranium nuclei. Okay, we can do this. We can describe the number of nuclei as D. Okay. And the solutions are written as, oops, this should be a 1. Minus plus. Okay, solving for the relationship, let's use some constants. So we're going to get H1 and H2 relationship. We'll use T1 half, T1 half, N1 at T equals 0, N2 at T equals 0, and N3 at T equals 0. So this will be 2.46 minus 10 to the 5th years. And that's for the uranium-thorium decay. And this one is 7.54 times 10 to the 4th years. And that's the thorium to radium decay. And this is the initial number of uranium nuclei. This will be thorium, and this will be radium. Okay. So we're going to use the initial condition of and then we're going to plug these into our equation. So N2 And this will equal, and then I'm going to have, this is, since this is 0, this will be h1 e to the 0 plus h2 e to the 0, and that will equal n10 times h1 plus h2. So we're going to equate this to 0 because there's no thorium initially. So we're going to have n10 h1 plus h2 equals 0. So h1 plus h2 equals 0. And h1 will then be equal to the negative h2. There's our A. Okay, and then let's go to B. Let me find B. B. This. Use the trial solution to calculate dNt over dt and substitute that into the differential equation for N2t. Collect the coefficients of e to the negative h, or excuse me. Okay, since equation must hold, for all t, each coefficient must be 0. Using all this, solve for h1 and complete determination of N1. Okay, let's see if we can figure this one out. I'm a little nervous. See what we can do here. Okay, we're still going to start with our same information that we started on the front. So let's differentiate both sides of this as follows. This is our equation that we're done with from the other side. This will equal okay. So there's our equation. And so we can get both sides, derivative of both sides here. So let's do this will equal okay. Then we can expand and get rid of coefficients here. So let me work on expanding this. And then I'm going to have to continue that right here. Okay. Let me see if I got that, what I wanted to get here. Okay. And then let's get rid of that N10. And then I'll have to change some signs here. So that'll get me to lambda 1. That will equal, again, I'll have to put this down here. So what can I get rid of here? Okay, so that'll end up with lambda 1 h1 e to the negative lambda t plus. Sorry about this. Okay, so we're right there. And we can isolate some terms here. So let's get to, finally, and then we can solve in terms of h1. Okay, and since h1 equals negative h2, h2 will equal positive. Okay, so those are my solutions here. I think that's what they wanted me to do. And then for C, what am I doing? At time 0, Pure sample of uranium-234. What mass of thorium-230 at T equals 2.46 times 10 to the 5th years, which is the half-life for uranium decay, uranium-234 decay. Okay, so we've got everything written down here. So we know that our half-life will be, or that constant 0.693 divided by our half-life. And if we know that that's, we plug H1 and H2 into the given equation, okay, so we're going to get times 2 point times 3.14 154, and that will equal 8.93 times 10 to the minus 14th seconds to the minus 1. Then we can, and that's going to be the decay constant. Then we can do this thorium to radium over, that'll be 7 point, and this will equal 2.91 to the minus 13th s to the minus 1. And then we can solve for H1, which we already have the, well, let me just do this. So that'll be H1 equals okay, and that will give me 0.4427. Then solving for H2, it'll just be the positive. And that will equal negative 0.4427. Okay, and then we have to consider the number of uranium atoms, so we'll get N10 . So N10, whoops, will equal 0.0300 divided by 234 times 1.67 times 10 to the minus 27th. And that will equal 7.68 times 10 to the 22nd atoms. So we need to plug our decay constants in. We'll get N2 sounds like you're dying. Sorry about that, folks. What was my H1? Oh, they're the same. Okay. Okay, and this will equal 1.35 times 10 to the 22nd atoms. And then let's get the mass of thorium. And that'll equal 1.35 times 10 to the 22nd atoms times 230 AMUs times 1.67 times 10 to the minus 27th. And that will equal 5.19 times 10 to the minus 3rd kilograms, or 5.19 grams. And I think that was it.